Okay, continuation with LP4. So I think we've stopped in this ring flip. So again, what makes a cyclohexane stable is first it can cause this ring flip. So that's why it's being discussed. What is really a ring flip? That is a switching between being an eggshell to being an equatorial, or being an equatorial to being eggshell. So that's why we were taught how to drone, or probably you should be familiarized, because as you really have to go back to this if they're discussing about eggshell and eggshell, or probably steric strains because of that position. So steric means how near a molecule with respect to another molecule. That's really the explanation I've been telling you about. Let's say medicine, how come one particular medicine would be effective with one another, because they have such an angle. If we can see these compounds in nature, we have to study them so that we can know them. So by looking at their properties, we will know how they interact because of those angles. So that's why we really have to pay attention with this, because that's how they interact with proteins in the in on usually on cells, which is the living things. So you have here, anyway, I don't have you really have to read. It only compares in terms of energy. So in terms of energy, it is telling us that that's what makes it stable, because it shifts. It shifts from being ring flip to, so even in the concept of resonance, the more it has resonance, the more it is stable. So this is a similar fashion. The more you have a contortion with itself, just changing position from the axial to an equatorial, the more it is stable, because of course it shifts because it has those strains. So if that is not stable, of course, because of those strains, it will break. So meaning those substances that contorts, but cannot really probably switch between somewhat stable or more stable um, positions, then they are not stable themselves. But if they can switch between somewhat stable positions, the more they can do that, the more they are stable. So that's what this discussion is telling us about the ring flip. So this is how it is for a mono substituted, meaning you have a one hydrogen substituted. This one is a halogen substituted. So that's what the explanation goes. The bromine is switches from here to there. And I think there's a discussion about energies, but anyway, that's what it means by discussing energies, by really pointing out that it is more stable than um, those compounds which don't have that six cyclo, meaning carbons on the chain. And then you have conformation for monosubstituted. So again, this is monosubstituted, and then the energy is being highlighted. So I think this one is an energy difference, delta E. So that's the energy difference when you try to plot that conformation as they twist. So this is really from researches or experiments, wherein they tried to plot, of course, with respect to R is a constant, T is what temperature were they conducting that study, and then K is um, your what do you call this? Uh, what do you call this? Constant. Your um, product constant. Meaning, if we try to look for the energy, the number of moles of product versus where it came from, so that's what that K represents. So meaning, the whole of that is really measuring that energy of those substances in terms of you have your moles and in terms of temperature, because that's what energy is dependent upon. So and then it is plotted. The plot is actually the difference between this one is the less stable isomer, meaning the conformation, and then this one is the more stable isomer in terms of conformation. So energy difference in terms of kilocalories per mole or kilojoules per mole. So the units here is kilojoules per mole, and then this one is calories per mole. So they are just measurement of energies. So the energy difference between axial and equatorial conformation is due to steric strain. So that difference actually is because of the steric strain. So as we've said, steric strain are the strain which is being experienced by the molecule itself because some part of the molecule on the contortion will be near with each other, just like this. So this atom in near with this atom exhibit that strain, that that strain, that steric strain. Okay, so this is how it look like in the um, energy density. I mean, electron density um, representations. What do you call it? And then you have, of course, how terms like gauge. It's already discussed in chapter 3, LP3. And then you have a monosubstituted, you have a disubstituted, you have a butane, and then in comparison with your methyl cyclohexane, and then you only have to read what does it says. Um, Steric strain in a monosubstituted cyclohexane. So meaning if you have a monosubstitution of fluorine, so these are the diaxial 1,3 diaxial strain is you have a position of 1,3, meaning they are separated by one atoms and then they are being compared. So this is the energies associated with that. Okay, so with different compounds, and then of course with respect to molecules, so because of the steric strain, so of course for your steric strain it will depend now on what molecules are those which are near, and molecules are atoms or group of atoms which are near on those 1,3 positions. Those 1,3 positions, there are these elements or group of elements or groupings, and then uh, how do they have what are the numbers in terms of their strain. So it somewhat measures that steric strain with respect to different groupings. So that's what that graph said. And then you have conformation of a disubstitute, meaning you have already two groups, two types of groups. So the first one is a monosubstituted, meaning your hydrogen on that normal cyclohexane, you have one other groupings. So one other groupings for the first one, you have a fluoro grouping, or the second one is a chloro and a bromo, which are somewhat similar. And then how about if that one grouping is an OH? So what are the steric strains? So that is a monosubstituted. For this one, that is substituted when you have two groups. Just for example, this one, you have a CH3 and a CH3, you have a metal group, and then it interacts. What are the steric strains? So these are the discussions with it. Okay. So you have also a ring flip, but of course the energies would be different for different kinds of groupings. So you kindly read those. I'm only directing you what does it mean in a general sense so that you can grasp. The same kind of conformational analysis is carried out for cis and trans 1, 2. So again, there's another comparison with respect to 1, 2. So these researches are somewhat ancient already, 1970s, 1960s, probably 19, or 1980s. So they are already computed, and we only have to know about them because they comes in with the explanation on how are they stable on how they interact. Okay, so you have a disubstituted OH and a CH2OH. So that is, I don't know, there are a lot of OH. So so you have an example of a sugar. So and then there's a discussion with it with respect to that things that they're talking about. So I think I've already read that one, but anyway, I'm just guiding you. And then this graph here is yun. Uh, you should go back here whenever they are trying to explain those things. Why? Because the cis-trans system is uh, are they how we represent it in a two-dimensional fashion. But of course, in terms of a more detailed discussion with respect to the ring flip, or probably that flipping for making it stable, then you must be talking about the axial and equatorial relationship. So this is a cis and trans discussion with respect to in comparison or in connivance with axial and equatorial relationship. So it says that for 1,2 cis and 1,2 trans, that is usually the normal. You withdraw kasi cis in terms of cis if they are both up or if they're both down. If trans, they're up and down. So in terms of axial and equatorial, for a 1,2 substitution, meaning they are close, so that is an AE or an EA. Meaning the first one is probably an A, an axial, and the other one is an equatorial. The second one, or the first one, it will be an equatorial, and the other one is an axial. So that is a 1,2. But that is not the case for a 1,3. Look at it. For a 1,3, the cis actually for an axial equatorial, 1,3 is both AA. So they are both axial. So it is drawn the same as drawn for a two-dimensional because we cannot usually use computers always. So we should we can at least we can already understood, or even if we have computers, of course the book is not three-dimensional. If they are written in papers or published in books, so you have to know that the 1,3 type is not like the 1,2 type, which are both which we can imagine that they are axial and equatorial. So that's what this table says. Okay, so you have to go back if ever there's a discussion about 1,2 cis, because they will be telling us this. If we will not go back here, or we don't know that idea, we may be lost. Okay, that's the point actually when we are not chemists after all. So we should only understand them on what they're saying, of course, so that we will be in one page. Of course, they're the one who are doing those things, exploiting those things, but what they're saying we should understand, because we are the receiver. Or probably me, I'm a chemical engineer. What the chemist does or biochemist does, we usually put it in a context of big plants. We will make medicines probably, or if we will make a particular food, and then we should interact with the compound chemically. So we use these knowledges. So the same as you, if you are a field of biology, so if you're talking about bioactivities, probably, so there's a discussion about, for example, one of your biochemical compounds as a bioactivity because of this. So you can go back, or probably you can understand what they're talking about, or probably you can explore more because you can understand anyway. And then as you can see, there are those energies. It just tells us which is higher, which is lower, and so on and so forth. And then you have conformation of a polycyclic molecules. Polycyclic molecules, of course, you have more than six. So it's already been lumped. The final point of the cycloalkane sequence is to see what happens when two or more cycloalkane rings are fused. So there are fused rings, just as the Benson rings are being fused. They are common really. They are fused because they are also stable. So while other compounds, fused other compounds is not also stable. Um, while the six is stable, so even the fused are also common in nature. So we have decaline, two fused strings. There's discussion. So you have to read those one. Transdecaline. See, these are common with respect to your this is testosterone, steroid, usual lipids of our bodies. Anyway, I have to cut the video. Anyway, there's no more actually to discuss. We're already done. Okay, thank you guys for listening.